Okay, I want you to open up this workbook, this Gibbs Ensemble Monte Carlo workbook. You might have to spend a second, download it from Learning Suite. We're going to go over the theory behind this today, but I want you to start a simulation because I kind of want to get multiple results that we can maybe show the class. And these take a little bit to run, so I want you all to just start them on your own machines. And so bring those up. Let's do 125 boxes per particle. It's about a good balance right here. I want you to just select some temperature range. I don't want everyone to select the same one. So change the temperature range and change the density range. And then you can use the slider bar, or I think you can actually just, you want to use the slider bar, I think, so it doesn't mess up the sheet. And then I want you to put the maximum cycles somewhere around 500. So select some sort of temperature, select some sort of density, and then give it a good amount of cycles. And then you just click Begin Simulation. And it doesn't look like it's doing anything other than you see a counter here. But you see that I'm on cycle 2, cycle 3, so it's going to take a little bit to get up to 500 cycles, 10 or 15 minutes. So I want everyone just kind of begin that so that we can see the results after we go through the theory. So just make sure you select a different temperature and density. Okay, I'm going to go over to my other computer and we're going to talk about the theory behind this Gibbs Ensemble. Chapter 8, Gibbs Ensemble. Last little part of this chapter. Gibbs Ensemble is a method that researchers came up with to simulate vapor-liquid equilibrium, the saturation line. And theoretically, you could probably do solid-liquid equilibrium too. Solid-liquid equilibrium is just not usually as important to us as vapor-liquid equilibrium. Well, you know that in vapor-liquid equilibrium, it's important for separations. It's important for designing, say, refrigeration cycles and for doing a variety, power cycles, all sorts of things that we deal with in real life. And we usually have to measure vapor-liquid equilibrium. We're not real great at predicting what the vapor pressure might be, or if it's a binary mixture, especially, we're terrible at predicting what the composition is going to be unless we have some sort of good activity coefficient model. And usually we get activity coefficient models from experimental data and then use them later. So this was a really big emphasis, maybe about 30 years ago, to develop methods to simulate vapor-liquid equilibrium. And one of the methods that came up with is this so-called Gibbs Ensemble. And the idea with Gibbs Ensemble is that we're going to simulate 2 boxes at one time. And we think if we pick the temperature and the density correctly, if we pick the phase point correctly, we're going to do this in a way that one of the boxes is going to eventually give us a liquid density, and one of the boxes is eventually going to give us a vapor density. Now, we're actually going to do this a little smarter than how I drew here. What we're going to do is, in essence, link the 2 boxes with some sort of diaphragm that can move. And so if the pressure on this side of the box got a little too big for the density that it might be, it would push this diaphragm over so that I always maintain pressure in this overall system. So I allow box 1 and box 2 to be in mechanical equilibrium. They're going to be at the same pressure because I allow this so-called diaphragm or piston to move freely. But I'm also going to make it essentially so that you can diffuse particles through here, or that the particle can transfer between the 2 phases. Not unlike if I had a piston cylinder that was full of liquid and vapor, we know the pressure is going to be the same in the system because it's all in one container. But then the mass will, some of it will be evaporating, some of it will be condensing at equilibrium. And I will establish, and I know that the chemical potentials have to be the same in that case. So what I'm going to do is I'm going to make a simulation methodology approach that allows the mass to move so that the chemical potential in both phases will become the same. And I do that by kind of simulating two simulation boxes so that if one box increases in volume, as I drew here, it was moving to the right, the other one would decrease the same amount, if that makes sense. That's how I link them so that they get the same pressure. If one increases in volume, the other is going to decrease, and it allows that mechanical equilibrium to occur. And then I'm going to allow the particles to move to establish chemical equilibrium, where I'm going to fix the total number, N1 plus N2 in both. So N1 plus N2 is fixed, is equal to some constant, but N1 and N2 can change. So I can lose a particle from, say, box 1, and it can go over to box 2, but the total number of particles has remained the same. This is what we're establishing is a grand canonical ensemble. We talked about the canonical ensemble. This is the grand canonical. And it sounds scary, but canonical ensemble, remember, is constant N, constant V, constant T. That's what we've dealt with most of the time when we've been doing simulation and what we derived in chapters 5 and 6 and 7. We always did canonical ensemble. Well, grand canonical is mu PT. I'm going to keep the temperature constant. I'm going to still let that be one of my things. But now instead of keeping the number of particles constant in a box, I'm going to keep the chemical potential constant. So the particles have to be allowed to move. And then I'm going to keep the pressure constant by allowing the volume to move. Last time we talked about the isobaric isothermal ensemble a little bit. So NPT, it doesn't have a fancy name like canonical or grand canonical. There's also a microcanonical ensemble, which is NVE. It's called the microcanonical. I don't know why. But when they were doing statistical mechanics years ago, they said canonical is NVT, microcanonical is NVE, grand canonical is mu PT, and then NPT we just call constant pressure, constant temperature ensemble. I don't know why they didn't give it a fancy name, but that's isobaric, isothermal, or NPT. Okay, so let's talk about how we get this to happen in the code. We kind of summarize these three moves I've talked about, maybe last time, in this idea of moving particles in these three pictures here, these pictures. We're going to have three types of Monte Carlo moves. We're going to randomly do these moves. We're going to randomly do the order in which we do them. But one of them is a regular Monte Carlo move, where I randomly pick a particle in the box and I randomly give it a displacement, and then I accept or reject that according to my normalus or my normal metropolis criteria. So exponential of minus beta delta U. So that's just the normal thing we've been doing for a long time. And I'm going to do it in both boxes independently, right? I can independently move all the particles in each box. So that allows each system to kind of move like it would normally. I have the volume displacement that we kind of talked about last time, where I'm going to propose that the box can get a little bigger. And if that one gets bigger, then this one's going to get smaller. But if I do delta V here in 1, delta V2 will equal minus delta V1. I'm going to randomly propose that the box gets a little bigger or a little smaller, one of the boxes, and then the other box will get bigger or smaller proportionally. That makes it so that these two are linked and they get to the same pressure mechanically.
Dr. Knotts,
Yeah.
A quick question about that. When you change the volume, are you changing the relative spacing, or like how do you account for like a particle being near the wall when you delete that part of the box?
That's right. So we talked about that a little last time, and we'll review it today. If I create a box, and I'm going to kind of deliberately draw these close to the wall, and then I wanted to make that smaller. I proposed a volume change that made the volume smaller. I got to move my particles. And so the way I do that is I scale all the particles so that they move in, so that they still would be relatively in the position where they were relative to the box edge. And the way I do that is written in the code we talked about earlier. I just need to figure out the ratio of this length to this length. And then I multiply all the positions in the XYZ by that length. So yes, I have to scale the positions. So when I do a volume change, I first randomly generate a volume change I want to move, maybe like, 1 cubic centimeter or whatever. It's never going to be that big because we don't have boxes that big, but 1 cubic angstrom. We're going to move the box in angstrom on a side. Then I would go in and shift all my particles, the ratio of 1 angstrom relative to what I was before.
Okay, cool, thanks.
So yes, I scale my particles. And so if this one's getting bigger, all my particles would kind of scale out a little bit so that they kind of all look, I want red, give me red. So they kind of all look the same. And then because this box was getting smaller, all these particles would get a little closer together. And so we've got those two moves. We kind of talked about both of these before, but then this particle transfer move is the last one. And then we'll go through the code to see how this works. Particle transfer move is I'm going to randomly pick one of the boxes to delete a particle, and I'm going to put it in the other box randomly. So in this case, I'm going to randomly pick this one in box 2, and I'm going to randomly put it somewhere in box 1. Now, for each of these moves, I have some sort of metropolis criterion that I got to make sure is satisfied. And so it's going to look like exponential minus beta, but then I've got it, it's going to be the total energy. I'm going to call that delta E for right now. And I just got to figure out what that delta E is. And this is what a lot of work has gone into. Technically, if you look back at this metropolis criterion, I could write this with a capital delta E for the total energy. So E is total energy here. Why haven't I needed to write total energy so far for the MC moves that we've done? I might need to ask that question a little later, but what's the kinetic energy?
Is it because like the two systems before and the other ensemble are like so similar that a lot of it just cancels out?
Yeah, so actually a lot cancels out. Like there's no kinetic energy, right? Before and after, the kinetic energy would be the same because we're not doing kinetic energy. And then there's no volume change, so there's no PV work. So before and after would be the same, so it would cancel out. When I start changing a volumes, I've changed my potential energy because all the particles moved, like we see here. So I have a delta U part, but then I also have PV work I got to take into account because I changed the volume. And so this total energy will also encompass that PV work part. And then down here, I have the delta U part because I moved particles, right? But then I'm also going to have a chemical potential part, a change in the chemical energy, and we'll kind of show how we do that. And it'll make, I think it'll actually make a little sense as we go through it. So we technically always have to do the total energy change, but when we were just doing particle displacements in a single box, that's all the energy there was. There was only potential energy. So I only had to write delta U. When I move a volume, do a volume change, now there's potential energy changes and PV work changes. And then when I do a particle change, there's delta U changes and this kind of chemical potential work change of moving a particle. Okay, so let's go through some code now. Now there's actually, I want to make sure you see this in the book. The book forgot the negative signs kind of in all these metropolis criterions it puts throughout this whole chapter. So just know that you got, it's a delta, it's a minus delta, and just kind of remember that. How we're going to do this is, well, before I get to the code, let me do a couple other things first. So we need this exponential minus capital energy. This is what the change in energy looks like for a volume displacement move. So this part here probably makes sense so far. That's just because I changed the particles in each box when I scaled them. The delta U, this is the normal Leonard-Jones that we've already done a lot, but because all the particles moved because I scaled them, I got to recalculate the energy. And so there's a delta U for box 1 and a delta U for box 2 because I have a before and after. And so that's the potential energy change. And then this is the PV work part, which you probably can kind of see looks like a log of, V2 over V1 or V new over V old. It's like an isothermal compression of an ideal gas. If you think back to thermo, that's the PV work part of doing this. And so you can see that this is just the new volume for the first box, and this is the new volume for the second box. I increase the volume in one, I decrease it in the other. And so all this is fairly easy to calculate, right? The nice thing about this is I don't have to add too much code to my simulation to do these kind of moves. I still do the normal Metropolis kind of thing. I need to calculate energies, but I also then need to calculate this PV work that's fairly simple, right? It's just volumes over volumes and logs. I can stick that in fairly easily into my exponential. And then I generate a random number, see if it's less than e to the minus beta delta E, and then accept or reject. What about the particle transfer moves? So here's the E for the particle transfer moves.
This is all derived for an ideal gas.
So it's not an ideal gas, but all the non-ideal gas part is right here, right? That's the Leonard-Jones. That's how we're interacting right there. The volume stuff looks like an ideal gas.
Okay, cool.
So here's the potential energy part, because if I delete a particle, right, it changes the whole potential energy in a box. And if I put a new particle in another box, it changes the whole potential energy over there. So I have a delta U of both boxes. And then this may not look too familiar, but I want you to focus on this part right here. And then I'm going to write something that you may remember from thermo. The definition of chemical potential is dg dn at constant T and P or whatever. So what you kind of see here is this criterion has what the change is in my chemical potential, right? It's if I move a particle, how does G change, right? We literally move one particle. We're getting this kind of partial derivative idea. How's the free energy change as I move a particle? And I only move one particle at a time, right? So it's basically how many particles are in the new box and how many particles are in the old box. What was the work needed? And if you kind of go through all the math with this partial derivatives, you'll remember that delta G's have a lot of logs in them. And so that's where the log part comes in. And it's the log of this N over N. And so really what you're literally getting here is the change in free energy. Does the free energy go up or down if I transfer this particle? And if it goes down, then we're probably going to accept that, right? That's going to mean it's more favorable. If it goes up, we're not going to accept that all the time. It's going to be relative to its exponential minus energy. So make sure you kind of see the overall picture here. Is all we have to do is change how we calculate the energy that goes into our Metropolis criterion, but everything else kind of looks the same in our simulation. We still have to set up a bunch of particles. We still have to calculate the energy of them all using Leonard-Jones, right? That part hasn't changed. We have to add a little coding in to do a volume displacement and a little coding in to swap a particle. But once we do that, we just calculate delta E, calculate exponential minus delta E, generate a random number, and accept or reject, similar to what we've done for a long time. Okay, so let's go through some of the code now.
Quick question on the particle transfer delta E. Is that N1 going to be the total moles of the system? Or how does that relate to the moles of the box that's gaining and losing?
Oh, that's a good question. I think that's a mistake. I think that's actually N total it should be. I'll have to double check on that.
Okay.
Let's see what happens in the code. Let's see what it looks like in the code, but I think that's N total because it doesn't make sense to be just N1. I don't think. So let's go through here and we'll see what the criterion looks like in the code, and then I'll double check it when we're outside of class. So here's the first part of the code that's changed in order to do this grand canonical or this Gibbs Ensemble Monte Carlo. We have to first select, every time we go through an iteration, we first want to select the type of move we're going to do. Are we going to do, a displacement move, a delta V move, or a delta N move? And what we found is that we want to do a lot more displacements than we do volume or particle transfer moves. So one way we do that is we define a cycle as a number of displacement moves, let's say 80. And then we might want to put this at 10 at 10. So we do maybe an 80, 10, 10%, 80%, 10%, 10% distribution. There's nothing necessarily special about that. And you could do some work, and I'm sure it's out there, I just don't remember it all, where people have gone through and said, oh, these are the optimal ones to get the best results for the smallest number of steps. But for us, it's just, we can just do about 80, 10, 10. So I'm going to, in general, do 80 displacement moves, and for every 10 volume displacement and every 10 insertions, I try. So these are all just attempts, right? I might accept or reject them. And so the way this code works is that one cycle consists of this many moves, and then I randomly generate, I get a random number between, say, 0 and 100, or however I've set these numbers up. I can set them up however I want, but say 0 and 100. That's what N move plus N volume from N insertion is. And then I just say if it's less than N move, which was 80, then I'm going to call a move, a displacement. But if it's between 80 and 90, then I'll call a volume change. And then if it's between 90 and 100, I'll call a transfer move. You could come up with a variety of different ways to do this. There's nothing special about this approach. All it is a way that says I have some distribution I want to do, mostly particle displacements. And then, so I'm going to say, I'm just going to generate a number between 0 and 100, and then I'm going to call N move 80, and then N volume 10, and then N insert 10, and then this little approach will give me my 80, 10, 10 distribution. You could do it a variety of different ways. But the point is, I just want to call displacements more often than I call particle transfers or delta V's. So any problems with that? And we call that one cycle. So we're going to try 100 moves for one cycle, or 100 possible displacement, delta V and delta N. Okay. Well, that's kind of the easy part, selecting what move to do, but how do we do all this stuff about moving particles and changing delta V's, things like that? The way that is commonly done is we're actually going to not just keep track of 2 boxes, we're going to keep track of 4 boxes. Man, I can't even. These are going to hold the trial moves. So it's going to hold the energies and positions of the trial moves and the volumes and all the things. So we just need to keep track of, it's mostly a bookkeeping thing. We need to keep track of where the particles were if we changed a volume, right? Because if they change all positions, we need to keep track of it if we insert or remove a particle. So the easiest way to do that is just to have exact replicas of the two main boxes that we change according to whatever move we call. And so that's how this box, or that's how this coding is approached. To save us a little time, we also keep track of something called E-box, which is the energy of box 1, 2, 3, or 4. So it's just an array. I just need to keep track of them because I'm going to have to do delta U's. If you go all the way back up to these acceptance criteria, remember delta U actually has 4, delta U1 has 2 before and after, and then delta U2 has a before and after. So there's 4 energies I got to keep track of. And so energy box, E-box, holds those 4 energies. And then we design it so that box 1 and box 3 are the corresponding ones, and box 2 and box 4. So they're always displaced by 2. 1 and 3 are the corresponding boxes before and after. 2 and 4 are the corresponding boxes before and after. Okay. So here's how we would do kind of a normal particle displacement move. I put a for loop in where I go over box 1 and 2. So for box 1 and 2, remember displacement just means I randomly pick a particle or randomly move it, but I want to do that in both boxes every cycle. I want to allow them both to equilibrate. And so you'll notice now that my arrays for X, before I just had one index for, particle I, but now I have an index for box and then particle I. So I've made a 2D array. That's how I do my 4 boxes. The first index is what box I'm in. The second index is what particle I'm in. So what I first do is set box 3 and 4 equal to box 1 and 2. I basically just copy the positions over, if that makes sense. Then, so right here's box 1 and 2. This is box 1 and 2 because box is going over 1 and 2. But notice then I add 2 to box to get to box 3 and 4. That's how I do that. Does that make sense? So I just copy box 1 over to box 3 and box 2 over to box 4. Then I kind of start doing my moves. I randomly pick a particle. Random particle. And then I give a random displacement to that particle. This is similar to what we've already done for a long time. I have some sort of max delta. I generate a random number between -1 and 1, multiply it by that max delta, and then add it to the particle current position. But you'll notice I'm storing that in box 3 and 4. Does that make sense? So I didn't change box 1 and 2. I just changed the position in box 3 and 4. And then I have to do my normal periodic boundary conditions, right? If it goes outside the box, I got to put it in on the other side. So I do that kind of normal thing. And then I need to calculate the energy of this new box. I changed a position in it, so now I need the new energy. And I have a subroutine where I send it the box number and it returns the energy. And let's just, I'm going to skip down to this real quick. Where is that? Oh, it might be up. Give me a second. It's actually up here where we were doing box changes. And that energy subroutine just loops through all the particles. Where is that little subroutine? No, sorry, I don't have it. I thought I had it in, I thought the code was written in here, but it just goes through. Let's get back to where we were. I'll just kind of write pseudocode here. So energy would look something like 4I equal 1 to n minus 1. And then 4j equal I plus 1 to n. I would first calculate Rij and then do Leonard-Jones, where I have 4 epsilon, or 4 times r plus to the minus 12 minus r plus to the minus 6. And then I'm adding that throughout the whole loop. But I'm doing my r's based on whatever box was sent in, the box number. And so it would be something like x box number, comma I, minus x box number, comma j. So I just changed my energy subroutine, this double loop, so that it's doing positions for the box that I send it in. But it's the normal Leonard-Jones type summation thing. So energy box. So after I called energy, I stored it in that array E box. And remember, E box was an array with 4 entries. And so that allows me to calculate the change in energy for the 2 boxes. This is delta E, delta U for box number, say 1 and 2, is equal to U box 3 minus U box 1. And then delta U box 2 is U box 4 minus U box 2. Remember, I stored my proposed positions in boxes 3 and 4 so that I can do my delta U's. My previous energies are stored in box 1 and 2. My new ones are in box 3 and 4. And once I have this energy, once it goes through this loop twice, oh, sorry, we don't need to go through the loop twice. It's just doing it box 3 and 4. I do my normal metropolis criterion, e to the minus beta delta U. I generate a random number. If my random number is less than that, I accept. So then I write my positions that were in box 3 and 4 over to box 1 and 2 because they become my new position. And then I also write the energy for the box back into the array. So I never have to recalculate the energies for boxes 1 and 2. I store those so that I only have to do 1 energy calculation per box. Does everyone see how that works? I kind of have 4 boxes, 1, 2, 3, 4. 3 corresponds to 1, 4 corresponds to 2. I keep all my new stuff in box 3 and 4 so that I can calculate the energy for 3 and 4 to get my delta energies. So that's the particle displacement. What about this volume displacement? Similarly, I'm going to first generate a delta V. It can be positive or negative. Remember, RND gives me a number between 0 and 1. I subtract off 0.5, so I get a volume change between minus 0.5 and 0.5. Now, I would have added, I would have done this between -1 and 1, but there's nothing special about this because Vmax will just change to make it a little bigger, a little smaller. I guess what I'm trying to say here is we could have generated a number between -1 and 1 and then multiplied it by Vmax. But for some reason, this code just did it between -0.5 and 0.5. But that doesn't matter because Vmax is going to change to give us a good acceptance probability. So the big thing is I generate a delta V. It can be positive or negative. And because it can be positive or negative, I then am going to say in box 3, the volume is a little bigger or a little smaller, and then it's the opposite of box 4. But I'm adding delta V to box 3 and subtracting delta V from box 4. But if I had a negative delta V, then I would be actually decreasing volume 3 and adding to volume 4. Does everyone see how it's going to be random? I'm either going to increase or decrease any one. The point is I'm not always increasing volume 3 and always decreasing volume 4 because del V can be positive or negative. So that's the first thing. I generate some sort of volume displacement. I'm going to increase box 3 and decrease box 4. Then I need to get the new lengths, or they're called cube in this code, remember. So that's just L equals V to the 1/3. I need it for box 3 and box 4. I also need L over 2. I need that to calculate minimum image. And so I calculate L over 2 for box 3 and 4. Now I've got to get that energy for the acceptance criteria. I have to calculate this. So I need the change in potential energies, and then I need these delta volume change terms. And so that's what we're going to do now in this subroutine. We're going to loop over both boxes because remember there's a delta U1 and a delta U2 in that acceptance criteria, and then there's a V2 over V1, or V2 old over V2 new, and there's a V1 old or new over old. So I got to loop over both boxes to get this acceptance criteria. I first need to scale all the particles. So I figure out what the scaling factor is. And this comes out to just be L over L, basically. But it's basically, remember, this is box 3 and 4 over box 1 and 2. I'm getting the scale factor. And then I just multiply the positions in my box by the scale factor for that box. So if my delta V for box 3 got bigger, if I increased it, then all the particles will move out a little bit. And I'm storing that in boxes 3 and 4. So again, box 1 and 2 doesn't change. It's the old positions. Box 3 and 4 are the new positions. And then here is where I'm doing this, these log terms that were in the acceptance criterion. But now I also need the delta U terms. And so I've got to call my energy subroutine for each box, 3 and 4. And remember what energy does, it just goes, loops over all the particles, does the Leonard-Jones, and gives me the total potential energy of the system. And I'm doing that for boxes 3 and 4 because I already know what they were for box 1 and 2 from the previous iteration. So that now I can get, this is minus, this is delta U here. And I've multiplied it by, and this is the beta part. And then here's my negative delta E over T exponential. And so you want to make sure that you see how here's the PV part and here's the delta U part of the acceptance criterion. And the delta V part, delta U plus the delta V PV part gives me my delta E, if that makes sense. But then I do the normal thing. I generate a random number. I accept or reject. If I accept, I copy the box 3 and 4 stuff that had the proposed position over into box 1 and 2. So that's now the new state of the system. And then I also write the volumes to the sheet. For some reason, this just writes them to sheet rather than keeps them in the variable, keeps a variable in the memory. But I think it writes it to sheet so that you can print it later and it shows the graph. But the bottom line is I just write the new volumes over somewhere so that I can keep track of them. Let's do the last thing and then we're going to go and see how your simulations ran. The transfer move, we need a little bookkeeping. And so let me draw this out to explain why we need a little bookkeeping. I'm going to kind of draw out a sample array or a few rows of a sample array for positions. And so we have 1, 2, particle 3, particle 4. So this might be X. The X position might be 1.5, 1.4, 3.8, whatever, and 2.4. Let's say I randomly pick particle 2, and the code calls it the chosen one. They're chosen. So let's say I randomly pick particle 2 in this box to get deleted and added to particle or to the other box. What I want to do is now make my array look like this. 1.5 would still be here, but now 3.8 would be in the second position and 2.4 would be in the third position, and then the other ones would fill in below. Does that make sense? If I delete the particle, if I delete particle 2, then particle 3 becomes the new 2, and particle 4 becomes the new 3, and so on and so forth. So when I delete a particle, I want to transfer all the positions up a little bit. And this code is going to do that. Does that make sense? When I add the particle, the other box, if you're adding it, that's easy. I just add it on the end of the array, right? I just increase the array by 1 row, and then it's easy. But deleting, I got this bookkeeping thing I got to do. And so here's how this is how the move works. I generate a random number between 0 and 1, and then I just say 50% of the time, I'm going to say box 1 is going to increase, or it's the get box, increase n by 1. And then box 2 will decrease. Right, this is just a little code to say particle 1 half the time, or box 1 half the time is going to get the particle, and box 1 half the time is going to lose the particle. So that's the first thing I do. Pick the box and pick whether it loses the particle or gains the particle. We have a little check in here. If we delete the last particle, if say particle box 1 or box 2, if they only had one particle to begin with and we delete it, we're going to stop the simulation because something messed up. We don't want to take the last particle out of the box. Does that make sense? And so we kind of have just a little error check here. But if that error check is fine, then we're going to randomly pick a particle. And notice here that there's an array n that just keeps track of 4 boxes. And it's the number of particles. I might start with, 500 here and 300 here. And then my new ones might be 499 and 301. Does that make sense? And it's just a 4 by 1 array that keeps track of the number of particles in each box. 1, 2, 3, 4. So I generate the chosen particle. And then I say boxes 3 and 4. I set the n for box 3 and 4 from box 1 and 2, whether it's increasing or decreasing. So I keep track of boxes 3 and 4 that, oh, this one increased or this one decreases. Does that make sense? So I write those 2 entries in that array. Now I got to do this little bookkeeping for the lose box case. So I'm going to loop around all the particles in the lose box. And if this is I less than chosen, then boxes 3 and 4 are just equal to the exact thing in box 1 and 2. That is this line that I just drew. I want to do a different color here. If the particle is less than the chosen one, then I just write that in the same position. Does that make sense? But if the particle is greater, if I is greater or equal to chosen, then I need to shift everything down by one. And the way I shift is say, I look at the particle, sorry, one position down, and when I write it to box 3 and 4, I don't put it in one down. So you have an I and an I+1 issue there. Does that make sense? And so this says 3 becomes 2, position 2, and 4 becomes 3. That's how I do that. So this is 3 goes to 2, 4 goes to 3, and so on and so forth. Okay. And then I need to calculate the energy. Remember, this is just my energy. This is my, this will give me my U of box 3 or box 4. And then I need to, so that's for the lose box. Now I need to add the particle to the get box. And that's the easy one. I don't need to do any bookkeeping really. I just have to add, so So first I copy box 1 and 2 over to box 3 and 4. And then I add the last particle in to the get box. And I randomly put this XYZ position in the new box. So remember, the get box could be box 3 or 4. And all I do is I put it at the bottom of the X array there. I just add a row in. I call it last. The last is the number it used to be, right? +1. So I just increase the row. That's where I increase the row. And then I randomly get an XYZ to put it into that last row. Notice that's not in a loop. This does 1, 2, this loop does 1, 2, and old in the box. And then I add 1 to that number and old, and I put a new XYZ in. But then once I have the new positions, I call energy to get U new for the box so that I can then do my delta U's. And so notice here, I'm going to now calculate this acceptance criterion or this energy right here. I need my delta U's. I need this log V over V. And let's make sure, Nathan, we check whether that's N1 or N2 or N total. And so here's my delta U part of that, delta U1 plus delta U2. Here is my log V over V. And where is this? Oh, you actually have N over N. I don't think this N is even supposed to be here, Nathan and everyone. This N right here in this acceptance criteria is not there. It's just KT. And I'll double check that, but I'm pretty sure that's what it is. That N's not supposed to be there. It's not in our acceptance criterion down here. Once we get our total delta U part plus our delta, this is kind of the delta potential or chemical potential part. I've got my exponential minus delta E beta. I generate a random number and I accept or reject. If I accept it, I write all of the box 3 and 4 stuff to box 1 and 2. And then I write the positions, X, Y, Z, that were in the proposed 3 and 4 box to boxes 1 and 2. That's that. I have to do that for the last one, and I have to do it for this one. I update all the energy so I don't have to recalculate boxes 1 and 2. And then I store the number of particles to the sheet so I can graph those later. but this is kind of the normal thing we see over and over in terms of procedure. I randomly do a move, which affects all the positions. I store those new positions somewhere. I accept or reject. And if I accept, I got to write the positions I proposed into my current array, so that the next time I go through my iteration, I've got that information. So that's the code. But now I want to talk about some of the results. And then I'll give you some time to ask questions about your homework you have. So any other questions about the code part? I'm going to go over to my other computer for a second. So here's what my simulation came out to look like. You'll notice that I have two densities, one high density and one low density. The high density will be the condensed phase. The low density will be the density of the vapor phase. And so for my condition where I selected a temperature of 1.12, I picked, it must have been in the two-phase region. Did anyone run their simulation and get it so that they only had one phase?
I did.
Do you want to show yours?
Sure.
I'll stop sharing and. Yes, so you picked a very high temperature, relatively, you don't know that, but the
Yeah.
critical temperature of a Leonard Jones is somewhere around like 1 point something. It's less than 2.4.
Mm-hmm.
And so you are in the one phase supercritical region, and you can see both boxes converge to the same density. And that's actually good. We want to see that. That just means we're in the one phase region. In fact, I'm going to bring up my textbook here in a second, and I'll show you that. Anyone else get a two-phase one that wants to show theirs?
So I think I did, but it looks a little more variable than Nathan's. I'll just show it. Or I guess this is a single phase,
Ooh,
sorry.
it's right. We might need to simulate yours a little longer. It looks like it might be trying to phase split,
Right here.
right?
Yeah.
And so let me show you my screen for a second, and then someone else get ready to show theirs. Because let's talk about what we're seeing here. And this is great. I wanted to see this. So I have clearly two phase, but people have actually mapped out the PT diagram or the rho V diagram for Leonard Jones. This is the two-phase region here. And so here's the condensed phase, right? This is the high phase. Here's the low phase. As I increase temperature, it looks like the critical temperature is about 1.32-ish. So anytime you put any temperature above 1.32, you should be one phase. So what Nathan was it that had the one phase? I think it was Nathan. Balich?
Barrett, first one.
Yeah. Nathan Barrett had the distinct.
Oh,
two-phase
that's
one.
right. You had the
One phase
distinct one phase that was like 2
Yeah.
point something. So you're way up here in the supercritical region. And
Yeah.
so that's why you see one phase. The other Nathan, where was yours? What temperature did you put?
1.6.
And so
and-
you were just a little above. That's why I was probably having a hard time. Did anyone put kind of something that was a little close to the critical by chance? Somewhere around 1.32? Anyone else have a two-phase one? No one else wants to show theirs? Let me show this for a second. I want to see. I'm going to restart mine. And I'm going to just end it after a couple cycles, because I think what some of you saw was the boxes changed positions. Maybe one of the Nathans want to show theirs again. I don't know if mine's going to show it well enough. Why don't one of the, because I think we saw it in one of those. Why don't you, Nathan Barrett or Balich?
I already started rerunning mine at a smaller temperature.
Okay.
I can share mine. I haven't run anything.
Okay.
What do you want me to look at?
Yeah, so look right here. Do you see how initially the dark blue one was above the lighter purple one at the beginning? Oh, at the very beginning, it looks like it flipped. But the bottom line is sometimes the dark blue's on top and then sometimes the purple's on top. Does everyone see that? And the two colors represent the two boxes. And so what you see sometimes as these things start out is there's nothing that restricts one box from being the liquid and one box from being the vapor. And so they sometimes change identities. But eventually, if you run long enough, they should kind of stabilize out to get one's the liquid and one's the vapor. Does that make sense?
Is that what was starting to happen?
I think that's what's starting to happen right there.
Okay.
Does anyone else have ones that kind of show that?
Dr. Knotts, I have one. So I've run several of them. Most of mine have been boring, just one phase. I did like as high of a temperature, like the 4 or whatever, and that one was just kind of boring. But this one, I have it right at the critical temperature, and it hasn't been going for very long. But as you can see that it definitely changes which one is on top and which one's on bottom. And it looks like it's just now really starting to phase split. This is at the critical temperature.
Yeah, so there, and I don't know exactly what the critical temperature is. I can't remember exactly. And it's also dependent on what your cutoffs are and things like that, because it changes just a little bit based on that. But if you're just a little below the critical temperature, then it will still phase split. If you're a little above, then you'll get just one phase. But that's what you're seeing right here is it looks like it's starting to finally decide it wants to be 2-phase.
Yep. So I had a question. Both of these like percent acceptances seem like things I could set, and they also change. So if I like set a percent acceptance, does that change the temperature or density, or what does that do? Or just
no, if you change the percent acceptance, it changes how big of a volume change or you do. You can't really do anything for the transfer move acceptance because you're only just moving one particle. There's nothing to change there. But remember, when you do a particle displacement, you randomly pick a particle, randomly move it. I can move it a lot or a little. And the less I move it, the more likely I'm going to accept because I probably haven't disturbed any other molecules. And so remember, what we do is on the fly, the code looks at maybe like the last 100 steps or whatever and sees what the acceptance criteria or the acceptance rate was. And if it was too low, then it increases it a little bit. If it's too high, then it decreases the maximum delta a little bit. Okay. Same with the volume change. If you can select an acceptance, I think that's when you move it, it sets it. I say I want to get 50% or 20%, and then the code will start changing the max delta V and the max delta move to be one of the so that it homes in on whatever you set it to be. I think by default it tries to be around 50%.
And look at that, Dr. Knotts, it switched again.
That's right, it switched again. You're probably so close to the critical that you're just seeing huge fluctuations.
Yeah.
It's actually real. This is, I think, kind of cool to see. You're seeing what criticality looks like. Did you guys ever see the movies of critical opalescence and thermo? Did we ever talk about that in this class? Sometimes I talk.
I do not think so.
You guys did not see critical opalescence? Oh my goodness. Let me see if I can pull this in, because this is a huge thing. What we were just witnessing with MATS is what huge density fluctuations. And that's what happens near the critical region. You get such huge density variations because it can't decide whether it wants to be a liquid or a vapor or a single phase or a double phase, that the fluctuations in density are actually become bigger than light, the waves of light, and it scatters it. And so you get this cool effect called critical opalescence. I'm gonna have to go to my thermo notes. I haven't taught thermo for like 10 years, but let me see if I can find one of the videos of that.
I had a question while you're looking that up. There was the book mentioned that the reason why we make our initial setups out of lattices is because if you try and do random placement, once you have a high density and you already have placed a lot of molecules into your box, that the last few molecules are really hard to place without having overlap. So I'm wondering how you deal with that with when you're taking one particle out of a box and putting it into the other one.
It's super hard. And so you'll notice that the more dense you are, the less efficient particle transfers become. And you have to simulate longer and longer. That's one of the challenges of doing any particle transfer move. And so the particle transfer moves for these really dense systems down here are going to be way harder to get a particle in. You're going to have lots of rejections from that than, say, things that are less dense. And so it's actually fairly easy to transfer a particle from, say, the liquid phase to the vapor phase. It's way harder to transfer from the vapor phase to the liquid phase. So the percent acceptance are usually low. And you can kind of see that here. I'm only accepting 14% of the moves for particle transfers. It's just hard to get those to happen. Now, there are some advanced methods. They're called configurational bias that we don't go over in this class, but when you start doing Monte Carlo for research, you would be definitely using these types of moves. And what you do is you kind of map out where the void spaces are initially. And so that takes a little time in your code, but then you preferentially kind of put the particle where those void spaces are. Now you bias the simulation like that. So you have to take out that bias with some fancy things. And we know how to do that, but it just increases the computational cost. But overall, if you go through the effort to do configurational bias to kind of map out where the void spaces are and bias your positions to putting them there, then even though it takes more time per iteration, you equilibrate the system much faster. So the overall wall time is faster. So yes, you're right, Ken. It's good that you picked up on that. The denser my system, the harder it is to randomly put a particle in. And then, so we do have some advanced methods to deal with that, but it's kind of beyond the scope of this course. Unless someone wants to do it for kind of their term project. Okay, let me show you what critical opalescence looks like. I got this video here. This is one of them. Let me skip back here. Okay, so this is, do you see the interface right here? I don't know if this, I think it's like sulfur hexaf. Oh, this is CO2. So they put CO2 right in the supercritical phase and they start heating it up. And what you eventually see is that the meniscus between the vapor and the liquid phases just disappears. I'm just going to kind of drag the thing over a little bit so you can kind of see how it just kind of disappears. And let me just pause that here for a second and look at a two-phase diagram. So what they did is they started at a key spot right here, right below the critical temperature. So the overall density of the system would have been like 0.33 if this was a Leonard-Jones system. And then the density started here and here. Then they start increasing so that the position of the meniscus doesn't change. You're still keeping the relative amount of liquid and vapor. If I had started over here and done that, it would fill up with a vapor, right? The meniscus would go down. If I started over here, the meniscus would go up. It would fill with liquid. Does that make sense? But if I start right kind of here, then I can keep the position of the meniscus relatively constant, if that makes sense. And now, so right now in the video, I'm up here. I'm above the critical temperature. Let me drag this over here so I can keep talking. So I'm somewhere up here. Now I'm going to start cooling it down. And right when it gets here, you're going to see what's called critical opalescence. It's going to kind of look like an explosion. So right here, we're in the supercritical region. It's just one fluid. We don't know what it is, and they're cooling it down. Oh, they're just starting. Let me go back just a little. You see it right here. You see this critical opalescence as it gets right at the critical point. The density fluctuations are so big that it scatters the light. And then you form your meniscus. And it's called critical opalescence. It's kind of a cool feature of criticality. And so again, what they did is they started in the two-phase region, they heat it straight up and they position it so the meniscus stays about the right position. But you see, right, as it cools back down, there's so many of these huge density fluctuations. The system doesn't know exactly where it wants to be. And it takes a little for it to kind of get back to its normal state. And I've always thought that's kind of cool. I've got another one. I think it's kind of cool too. Let me see if, oh, this is the dumb one. You can't see anything on that one. This one right here. Let's see. Oh, I know it's an MPEG. It won't play. Sorry about that. But it kind of shows the same thing, but it shows a bigger explosion. It uses sulfur hexafluoride, and it's a little more dramatic. And so what Matt was seeing in his with the densities just fluctuating everywhere and even the boxes change positions again, it's because naturally the density fluctuations want to do that near the critical region. And then you see this cool critical opalescence that happens. Okay. Any other questions on Gibbs Ensemble? You have a homework problem where it makes you just run this, so it might take a little while. You might want to get it set up and running so that you can do other things while it's running. But the big question on homework is this one. Has anyone started this problem?
I read it yesterday and got stressed out because I didn't know how to do it.
Yeah.
Okay.
I floated the whole thing.
So I want to relieve your stress a little bit. So let's just talk through some of this. If you need to leave, I know it's getting close to end of class. You can leave if you want to. I don't think graduate students, I think we don't have seminar today, right? Because we had 2 last week. Isn't that right? Anyone know? I think last week we had 2, so they only, because we had 1 on Tuesday, 1 on Thursday. I don't think there is one this week. So, but I'll stick around if anyone wants to keep talking about this. So what I want you to do here is add an association site to to the particle. And this is kind of maybe to model something that's similar to hydrogen bonding, or you can think of it like hydrogen bonding, right? Where if 2 water molecules have to be in the right position to hydrogen bond, they have to be in the right angle position and the right distance. And then they kind of lock in there for a second, right? They like being hydrogen bonded. You get this favorable thing. Well, one way we could do that is by adding a square well potential to our normal Leonard-Jones. We just add it on top of normal Leonard-Jones. And remember, the square well potential says something like, if I'm less than some well width, then there's some sort of favorable interaction. That's this one, the bottom. If I'm greater than the well width, then it's not there. You just don't have it. So to do this, what I have to do is create an array that keeps track of kind of where these associated sites are. So my particles usually kind of look like circles, but now I need a little dot on the circle. And so how am I going to create a dot on the circle? Can someone give me an idea on how I could code this to figure that out? That's the first thing you have to do. First, you have to get the initial positions of the dots.
Well, I have a question, but my thought to answer your question would maybe use some sort of like radial position. So you could either do between like 0 and 360 to represent an angle on which it is.
Yep.
Okay.
And you already kind of know what the distance is, right? The distance is like sigma, the width of the molecule, or that's half sigma, the radius of the molecule, right? So I have all the positions of my particles already. I set those either on a lattice or I have it from a previous position, right? So I already have what the center of each circle is, each big circle. Now I just need to say, start at the center of that circle, go out the radius, sigma over 2, and then I'm randomly going to pick an angle on there. Does that make sense? And if you're in 3D, you randomly pick a theta and a phi. Does that make sense? And there's a variety of ways you could do that. You could generate a random number from a trig function, right? To get between -180 and 180. You could generate a random number between 0 and 360 and then change it over to radians to position it or whatever you want. But there's just a little trigonometry and generating random angles. So that's the first thing you do. You have to I would just make an array called, square well positions, SWX or what, an XWY and SWZ. And then I can randomly, I know where the center is. I randomly pick a distance. I randomly pick a theta and I randomly pick a phi. And then I can place the positions of each one of those black dots in that array, X, Y, Z. Okay. Nathan, let me get to your question before I forget.
I was just wondering, are we assuming that the positions of these sites are fixed, or are we going to like randomly move them every step?
Yes. And so then once you get them set, I'm going to have 2 types of moves. I'm going to have my regular move where I randomly pick the center of the big particle, right? The center of the light blue particle and move it. That's the normal thing. But I also need to move its associated site, right? So if I moved it 1 angstrom in X, then I need to move the little site 1 angstrom in X, right? So I'm gonna have to do that. But that would kind of keep the little black dots same relative position everywhere, if that's all I did. So I also have to randomly pick a particle and then randomly rotate that black position. And I do that the same way I kind of set them up initially. I would randomly say pick particle 10, and then randomly generate a new angle in phi and a new angle in theta so that it moves that black dot around on the surface of that circle. If that makes sense.
So you said randomly pick a particle and do that, but should we actually go through and actually change its rotation for every single particle for every step?
That the better way to do it from a Monte Carlo way would be to define a sweep as I propose n steps. I don't want to just automatically change the position of every one. Just like I don't automatically force, I'm going to pick particle 1, move it, pick particle 2 and move it, pick particle 3 and move it when I'm doing a simulation. I call a Monte Carlo sweep where I say, if I have 500 particles, I'm going to try 500 moves, but I'm going to do it randomly. So you always want to do it randomly. And so don't just loop through and say, I want to do it for everything. Just randomly pick a particle. And in fact, you can do this right in the same subroutine where you're already looping through and getting all the distances and doing all the normal particle moves. Does that make sense? If you wanted to, you could do it at the same time you move the position. You can move the position and rotate at the same time, and then you don't even have to have a separate subroutine and it'll run a little faster. That's how I would do it. You always want to make sure it's random, in other words.
Okay, so I remember you talking about the code where, like, you know, from 0 to 80 we do this, 80 to 90 we do that, 90 to 100 we do something else. Would it be something like that where we'd add in like a certain portion of the time we're going to rotate it?
What I would do is start with, that's probably not going to matter as much. You could do it like that. Like I only call a particle rotate like once every 100, but you don't need to do that. You could do the rotation every time you do a displacement, just to be easy.
Okay.
Let me show you. I would start with, if you're comfortable starting in or coding in C, you could use the LJMC code. So some of you took C programming, like CS142, you could do it that. Or you can use the VBA codes that we work with. And I would start with, I think it says to start with the MC RDF code. And so I just want to bring that up for a second. I think it's coming. So because we eventually want to compare the radial distribution function with and without this little extra site. But if we look at the code for this, I might have to copy it over to Word for a second. So just give me one. Let me kill this one so I don't have as much stuff to worry about. And so I think most of the stuff you're going to deal with is going to be in this move subroutine. So I'm going to copy that over to Word just so we can zoom in a little bit. Okay, notice in move, we ran it for, we call a Monte Carlo sweep n possible moves. So if n's 500, I would try 500 moves before I go through the next iteration, but I randomly pick a particle. I randomly give it a displacement. We're kind of good at that, right? And I have to do my normal PBL, PBC, nearest neighbor type of thing. What I would do is I would probably just right here have something like square well X new and square well Y new and square well Z new, where I generate a new position here. And it's not going to be exactly the same as just choosing a random number and giving it a delta. It's going to be choosing a random theta and phi, moving the position of that particle relative to that. Does that make sense? So I would just do it this, I would just stick it right here in this subroutine. Then it's kind of easy to do. Does that make sense? And then down here, this is the loop right here where we're doing all of the Leonard-Jones, right? dx, dy, dz for the old and new. I would just have to add in more lines here to do the square well part. Right? I'd have a d square well x, or square well x, is equal to swx new minus swx old, and then I could, of the neighbor, right? I'm going to have all this sort of stuff here, and then I'd have to take the absolute value of. Right, so I can just kind of copy this. I'm just doing it with another array of data that's keeping track of the black square well positions. And then I tell you, here you calculate R squared, and then you stick it into Leonard-Jones, right? This Leonard-Jones code. But what you want to do then is add another line that where you would stick that position into some code that did this. If R is less than 0.3 sigma, I give it some favorable energy. And then if not, I call it 0. So that if you just add that, once you get delta U, you can just add delta U square well onto this. And then all of this stuff doesn't change, right? I generate a random number. I do my metropolis criteria. I can accept it true or false. If it's true, then it will automatically write all the new particle positions. And then I can write x square well for particle equals x square well new, and so on and so forth. So almost everything you have to change is in this one subroutine. You just have to code in the stuff that does the square well. So I need an array that holds the XYZ for the square well, an array that holds the XYZ for the new proposed, and then I got to code up how to add that to my energy before and after, if that makes sense.
So can I ask you another question that is unrelated to this one, but it's related to the homework? I just don't know. So I have my I have my this thingy. This is my number 3.
Radial distribution function, yep.
Yep. So these are my radial distribution functions. How do I get these into like a comma separated file or something like that that I can like use?
Do you have WinSCP? You're on a Mac, right?
Yeah, I'm on a Mac, yeah.
Do you know how to copy the... If you just copy this, can you paste it into a Word document? Does it allow you to do that? Just drag across that?
Yeah, more or less. I did it. Yeah.
Can you do that right now?
Sure.
I just saved it as a text file, and then I imported that into Excel and then, it asks you if you want it to be tab delineated. And then after that, I saved it as a CSV. But I did all this stuff.
There's a variety of ways you can do it. See if you can just copy those 100 lines first.
Okay, let me go to, because I did it and copied it into my Python. Where's my Python code? And you just put it in a Word file?
I would put it into Excel. Then you could save it as a CSV file and read it into your Python.
Okay. So
but I can show you how to do that with Word or Excel pretty easily. If you've already copied and pasted it once, this is not too hard to do. There's a variety of ways you can do this, right? File transfer and file IO. You could copy it over to your local machine and then just open it in Excel, delete all the other lines, whatever. But
yeah, so I'm gonna paste it. Nice. So those are all within one. So I do like paste special or something like that, right?
Well, just let me see.
We're only seeing
I don't see your Excel right now.
Oh, actually.
Okay, yeah, go ahead and just copy paste it normal. Go to the, see where it had that, see that little box that popped up at the bottom? Oh, Paste options, yeah. Use text import wizard. And then click on delimited, click next. Yeah, it's already there. And then push space or, yep, there, just click next and then click finish.
Nice. Okay,
There
cool.
you go. You can delete that first column if you want.
Okay, cool. That is very helpful. Thank you.
Anybody else?
Yeah, I just have a quick question on number 5 again. Are we going to use the supercomputer to run that, or do we
You
just
don't
do-
need to. I would just, if you code it in C on LJMDMC, you could. Or you can, if you're going to use the VBA, the worksheet, you can just run it on the worksheet.
Awesome, thanks.
Okay, so
I have a-
oh,
Go ahead, Tyler.
Oh, okay. I have a question on, I think it's number 3. It says to like compute the pressure from taking the integral, but the equation it references only gives us Z. I think I've looked up how to convert Z to pressure, but it's just kind of weird where we're in dimensionless units that I don't quite know what to use for the ideal gas constant, or if that cancels out.
So in dimensionless units, Z, so in general, Z is PV over RT, right? So in dimensionless units, the R basically goes into the dimensionless. So it's P star V star over T star.
Well, we don't have
And the
in
V star
output,
you have
so
in the density, the dimensionless
so-
density.
So it becomes like dimensionless pressure over dimensionless density over dimensionless temperature.
That's
I
right.
think what I worked it out to.
P over
I just
rho
didn't know.
T.
My answer was like slightly off from what was being printed out, so I was worried that maybe it was somewhere in my conversion.
No, if it's slightly off, that's okay.
Yeah, I think I figured out it was slightly off because the code computes the pressure using a different
Yes, it
different
uses the
integration.
virial thing, which is the dot product of the force times the positions. We kind of talked about that last time. These are two different ways to get the same thing. And you want to see they're a little different, I guess.
Okay, thanks. A lot of time researching that.
So I'm a little confused about the T star. I was originally thinking that would be reduced temperature, but I don't know how those are related. Well, probably
It's not reduced temperature. Yeah, so it's not reduced temperature. None of this, whenever you see T plus, I noticed right here, I'm looking, sometimes I use a plus, sometimes I use a star. They use both of them in the literature. Let me bring up my other computer real quick so I can draw.
There's a document on Learning Suite that like lists all the dimensionless.
Oh, that's
constants.
right. Let's just bring that up. And it's also on the documentation for LJMDMC. Let me bring up Learning Suite real quick. There's a document on Learning Suite that explains all the dimensionless numbers. Down here, dimensionless quantities. It's from chapter 7. And it just lists them out here. So the way you get a dimensionless temperature is it's KT over epsilon. So the epsilon is from the Leonard-Jones, right? And then that's what dimensionless temperature is defined to be. Dimensionless density is whatever your real density would be times sigma cubed, or dimensionless energy. And so it is, all the Leonard-Jones stuff we do is dimensionless because it's easy to make it dimensionless. When you go to, Kyle, like when you do proteins, it doesn't make sense to make it dimensionless because I would have to say, okay, I'm going to make everything dimensionless relative to carbon, and then everything else is not one anyway. So it doesn't make sense. We don't think about dimensionless quantities when we're doing real systems. But with Leonard-Jones, we make it dimensionless. Or with polymers, we can make it dimensionless. Anything where the sites are all the same, we could make it dimensionless.
Okay, that makes sense. Thank you.
Nathan, I thought you had a question. Did it get answered?
Mostly, but I'm wondering for problem 3 where we're doing the LJMDMC. I remember you kind of mentioning in class that we should probably change our number of E steps and P steps.
Yeah.
Does it really matter what numbers we pick for those? I think you said like 10,000 and 20,000, but how would we know if you hadn't told us what to do for that?
That comes from a little experience. You don't want, there's a couple things you always balance is how long do you want to wait? And is the system equilibrated? When I do research stuff, it takes weeks on a lot of my stuff. And the way we check equilibration is kind of similar to what we saw on the densities on our Gibbs ensemble. They were fluctuating and then eventually they kind of leveled out.
Mm-hmm.
That's what we do in our simulations is we follow the energies or other properties and we see where they start getting to level. I just know that for Leonard Jones, no matter what you start with, if you do about 10,000 or 20,000 steps, you're going to get level.
Okay.
It's going to be equilibrated. It's not going to be equilibrated if you only did like 100.
Mm-hmm.
And I figured 10,000 or 20,000 will take about 1 or 2 hours on the supercomputer. And I thought that was a reasonable thing to wait.
Okay.
That's the only reason I picked that. You could probably get by with like 500 and 1,000 and it would probably be equilibrated.
Yeah. Okay.
Well, I'm thinking about that too. You probably also want to change. I'm going to bring up, let me bring up one of those input files.
Yes, ma'am. Robert.
Is that me or is that one of you guys that are?
It's Kyle, you're not muted.
Oh, Kyle.
Sorry, that's me. I have to walk away. I want to ask the question, so I wanted to.
Awesome.
Give me
Okay,
1 second
thank you
while I
so
bring
much.
up
I
one of these
appreciate
sample
that.
files.
You too. Bye.
You probably want to don't put this less than 25 for your radial distribution, or it might just take a little longer. It probably isn't going to matter for these smaller simulations that we're running, but you could change. I think I changed it on one of the examples to 2 because we were only running a minute. But I think when I ran this, and you want to make this probably at least 50 for Monte Carlo. You don't want to write too often to the screen or it slows down your simulation, if that makes sense.
Okay.
And it's not writing to the screen on the simulation and the supercomputer, it actually writes it to a file, if that makes sense. And then it's that slurm output file. But anytime you do file IO, it kind of slows you down, especially if you're doing it a lot. So when I do a simulation for my research, I usually try to make it so I only write to file once every half hour, just to reduce file IO. And so a lot of times what I do is I write, if I want to write a file more often than that, I write it to a big string variable. So it's saved in memory. And then I dump that whole string variable once every half hour.
Okay.
But you kind of control that output with that number there. Don't make it 1 unless you're kind of testing for a minute. I'd probably put it about 50.
Okay.